please leave them in the Discord channel. And the stage is
Perfect. Thank you so much for coming. Thanks to PyCon Lithuania for hosting me, accepting my talk. It's been a great time here so far. Yeah, I'm going to talk about how we're building climate services using Python over in Montreal. So this presentation is going to start with providing some context, looking at climate adaptation services, what my company has built with XClim and Finch, and then going over how we've made that a little bit more accessible and so on. So who am I? My name's Trevor James Smith. I am a research software developer, packager, maintainer guy from Montreal. I have a background in, I'm not a programmer by trade. I'm a environmental researcher with a background in looking at wine and climate change impacts. I've been playing around with Python for about 6.5 years, and I recently became a citizen of the Uzbek Republic. So what is Uranos? So Uranos, we're a nonprofit research consortium. We started in 2003 in Montreal, and it was created in response to the fact that there was an enormous ice storm in January of 1998. There was about 1.5 million people without power for a few weeks. The total estimated damage was about 5.5 billion Canadian dollars. Yeah, and we wanted to do is we wanted to be able to not have a situation like this ever happen again, because climate change impacts are very costly, and if we know that they are coming, then we can better adapt and plan around that. So our idea is to have a climate change adaptation think tank that was financed by the government and industry, and yeah, and to be a nonprofit. So what we do is we engage in climate change adaptation planning. We are a climate model data producer and provider, so we run our own climate model, and we also gather and collect climate data information, so observations and models, their outputs. And then most importantly, we provide climate change information services. So what is that? Well, we're going to get to that. So what is before we get there, so what is our climate situation? So it's pretty much an established fact that humans are having an impact on climate. This is statistically sound. Yeah, and these one of the ways that this can manifest is with extreme weather patterns, like the one that we saw in Quebec in 1998. Yes, so yeah, well, right now we're, as of last year, we were at 1.1 degrees of warming above the pre-industrial normal, and 1.5 is considered to be beyond a safe limit, so we are rightly concerned. Now, how does this become a data problem? Well, when we're looking at climate science, it is a big data problem. This figure on the right is an estimate from 2010 of what we were expecting to see in terms of climate data volume. So you can see that models in yellow are taking up a much larger, a very large and growing slice of this pie, as well as satellite and radar as our sensors become more fine-tuned and more fine-scale. It's becoming more and more of a problem just housing and accessing using this data. So yeah, then the reason why this is happening is because we have climate models that are being developed every year. There's more simulations, more experiments that are being run with these models every day. The models are becoming higher and higher in resolution, both for their inputs and their outputs. These are grids, n-dimensional, very costly to store and use. And then we also want to be doing specialized analyses with these and creating like things for personal use. And so just that involves accessing the data, and that's very challenging. So climate services, what do we do with climate services? We tailor objectives and information for different users, and then a user could be somebody who's interested in agricultural impact. It could be somebody who's in engineering, looking at bridges. It could be people who are interested generally in the climate. Yeah, and ideally what we want to do is we want to be able to take all this enormous data and turn it into things that people can use, so they can access, so that they can better plan their own objectives. Yeah, we want to make sense of big climate data. So what are these things that we are offering by doing this? So this is what we call them climate indicators. So things like how many hot days are there going to be in the summer this year? What's the average amount of rain that we're going to see in June? These are the things that are kind of useful for planning things like maybe your growing season. There's hundreds of examples of what a climate indicator could be. And then how we want to present that information is also very important too. So we can think of a map, we can think of a point estimate just with a bar graph, and then gridded values. And then those are a lot of the things that we can do. And sometimes we get questions about, well, I'm not sure what I really need. So then they need guidance from experts. So that's another thing that we end up offering. So what it was like in the 2010s is, at my company anyway, was we were dealing with legacy code that was written in MATLAB. There was no code review. There was issues with data storage, access, processing. We didn't really use any async, nothing like that, and we were constantly dealing with like the demand that was placed on us. There was just so much work to do and just not enough people to work on it. And I mean, bugs happen. Sometimes you just have to, deal with it and just say, "Oh, I'm so sorry, that data set's no good. Here's another one." And then the fact that we're dealing with things manually, it's slow. And then no software testing, no data validation really. It's a bit nightmarish. So this couldn't continue. So when we were negotiating a few years ago with the Canadian government to develop a website to help people explore climate data, we made it a point to ask, hey, can we actually put some money towards building our own library to help operationalize this and make this a lot more easier for us to deal with? And thankfully this was approved. And so what did we want to do? We wanted to number one, have something that can do climate indicators. We wanted to have something that could not be too bug prone, a lot less human error possibility. We needed to do ensemble statistics to mesh data together in a very smart and less error prone way. Models for the climate are just like any other models. They're prone to bias. They can be wrong, so we have to correct that. And there's lots of ways that are to correct that. I'm not going to talk about that because I don't want to. And then we had a lot of data quality assurance checks. And so what we wanted was something that was operational, that could run constantly, that was foolproof, and that could be very easily extended. So yeah, there is Python in this talk, just so you know. I just wanted to let you, just reassure you, it's coming right now. So why did we build this climate service library in Python? Well, there was a number of reasons. So Python libraries are robust. They're constantly being reviewed by other developers because of its open source nature. This is very similar to the peer review process that we're used to, and that gives puts a lot of trust in it. Readability and reviewability is also a factor too. We're also developers ourselves, so being able to look at this code and understand it and know that it's doing the job is very important. There was just growing demand for these things, and we wanted to be able to make sure that people could start helping themselves. So Python is very great for building UIs and things like that. And then the timing was right. There was internal and external pressure for us to drop MATLAB and find something a little bit better. And so, yeah, it was an opportunity for us. So less time writing code, more time doing the actual research. So we ended up with a library that we call XClim, and we wanted to name it Hailstorm, but unfortunately that was taken. Unfortunately, and as you can see, we love badges, we love conventions. It's going very well so far. This library manages to strike a nice balance between usability and extensibility, but most importantly, it's very fast for what we need to do. So how do we build it? We based our data structures on several open source Python libraries, so namely pandas, NumPy, Xarray. Has anyone used Xarray in this room? Fantastic, great. So you know how great it is. Good. Yeah, and so because it's based on Xarray, it's the convention to put an X in your name. So that's why we landed on that. But yeah, we built it to be an operational library, and so we built our algorithms based on more conventional libraries such as SciPy for statistics, scikit-learn for bias adjustment. Numba is a program that provides just-in-time compilation for a lot of the functions that do a lot of the heavy lifting, so that speeds us up quite a bit. Yeah, and let's see. And Pandas provides the base API for a lot of the operations, especially around calendars and time. Unit management was extremely important for us to ensure that what you're getting in is consistent and has the right dimensions on the way out. And so there's a convention called the Climate and Forecast Conventions, and we were able to integrate that into a lot of the outputs that we do. Pint is a library for just doing unit conversions, and if you're familiar, if you need to do a unit conversion in your library, I would highly suggest it. And we also use PyTest, and we're this is research software, so we're very, very focused on ensuring that everything that is running is constantly being tested and stress tested, and including our documentation. Everything that could be tested is tested right now. I think we just don't have fuzzing yet, but maybe in the future. So here's an example of a one-liner that is a very simple. It's a very simple climate indicator that looks at the depth of snow. So you can see at the it's just a if you're familiar with pandas, you have a resampling over a time frequency, you do a mean over time, and then you ensure that the units that are coming out are exactly the same. The main thing that is important is that at the very top, you can see that in the declare units decorator, there's a snow depth equals length. So that's just to ensure that the dimensions that you are using on the way in are properly defined in the metadata. So we have two ways of running the algorithms. You have the indicators, which is the module that has all the bells and whistles, has metadata standard checks, data quality checks, time frequency checks. There's missing data compliance, calendar compliance, which is very important for climate model data because they might not have a 365-day calendar. It might have 360 days or 366. It's a very big problem. Yeah, so ensuring that is correct. And then if you trust yourself, you can also just use the backend core API. Yeah, so here's an example of our units management. Here what I'm doing is I'm looking at I'm doing a growing degree days operation using degrees Celsius or Kelvin or Fahrenheit between all the different, between the input data as well as the thresholds. And in the end, we're getting exactly what we put in. So this is a fantastic sign. We don't have to worry about the units being wrong if our input data is not exactly conformant. And then we also have things that for handling our missing data. So if there's any time slices, let's say if we're looking at a year of data, if there's more than 5% of data missing, then we can say this is not a good year, we're going to drop it. And the tolerance levels, it doesn't have to be percentages. We have lots of different ways of calculating this as well. We also added a module inside that allows you to do very specific translation. So right now we support French, but it's built to handle pretty much any language you want. If you would want to submit Lithuanian, please. Yeah, so this is example here, and we can see this is just what you would get from Xarray. You have your units as days. The cell methods are, it's a summary over days. The history is there, which says exactly what you used, the version that was used, and then most importantly, in the metadata below, you have our long name, you have a description, and then you have the long name and description in French with all the information substituted in, including the proper conjugation. Yeah, and so here is an example of what we can get when we're doing multi-model ensembles. So you can have these, like what you can see on the left here is a 30-year average for all of Quebec, and then on the right is the simulations that are being used to generate that. But these values are just looking at Montreal. So yeah, it's quite powerful. All of these models maybe have different calendars, so making that all work together was challenging, but it works very well. Yeah, don't worry about the fact that like it's so extreme. This is like the most extreme scenario possible. There's still time to change. So we also do and then as I mentioned earlier, bias adjustment. So using like a train and adjust approach. If anyone is familiar with the kind of SciPy way of doing things, this is very important for correcting climate model data to ensure that the distributions are comparable to what we would find in reality. And we also do a lot of upstream contributions. So we've done a lot of contributions to X-array, a lot of things to CF-X-array, which is for unit compliance and metadata compliance in X-array. We fix bugs in X-array sometimes. We've even like contributed some things to NumPy, and we also do the maintenance for a lot of libraries that are associated with this. And that's great. But you know, what if there's just too much data that we need to crunch? So if that data could be spread across servers globally, the local computing power might not be powerful enough for the analyses. Maybe the user doesn't know anything about Python, so they can't really be expected to run our library. It could be maybe a biologist using R or a different language, or an engineer who just wants a number. And then maybe the user is just wants to look at some cool maps, you know. So, you know, like what do we do? Well, we can offer a whole bunch of things. So this is a kind of like an overview of the climate services that we offer. We offer the baseline tools. We have our own platform, which is called Pavix. I can talk about that afterwards if you're interested. We can also do dashboards. We can create, we call them climate portraits, but it's just like web maps that you can explore yourself. And then depending on what you need, it can be tied to the climate data that we have. It could be tied to climate data elsewhere. Yeah, it really just depends on what it is that you need. And so when people ask us for things, we can point them in the right direction. So one platform that's out there is called the Microsoft Planetary Computer, and we recently had XCLIM placed on there, so there's an example there of how to use it, which is very cool. There's a lot of global climate data that's directly connected there, so that's one way you could play around with it without having to install anything. Yeah, so that's there. And then if we want, we can use web mapping service, or we could use web services. So people are probably familiar with web mapping service. This is what runs in Google Maps. There's also other things like WFS, WCS, and then most importantly, web processing services, which is for running spatial analyses over the internet. And this is very helpful for people who want to serve themselves. So what we did is we created a web processing service called Finch. And so this is a way of running analyses over the internet through a microservice. And it's dynamically generated and tied to XCLIM. There's 430 indicators that are on offer right now, and we've been due to update it for a little bit. Yeah, and so if we wanted to use it, it's very similar to how you would call it from XCLIM. You create a connection to WPS service. You can use a remote data, and then you call it almost exactly the same, and then you get your response, and it can be an object, it can be whatever you need. This is just an example of the website. I encourage you to check it out if you want. And you can see that there's lots of ways that you can run all these XCLIM indicators. It's very, very, there's advanced ways of playing around with it, and there's very easy ways of playing around with it. I feel that they've done a very good job putting that together. And so, yeah, just to like end here, like modern day climate services has been very revolutionary for us. Open source has been fantastic. Collaborating on lots of things in common has been great. We are using testing and CI. We have peer review for our software too. So that's been good. Thank you so much, Achu. Take care. Yeah. Oh yeah.
So does anyone have any questions? Okay, there's one question in our channel. So Arnold asks, can you use the system in Lithuania?
You could, yeah, you actually could. So if Lithuania has their weather data, if it's accessible, if you can get it streaming, or if you can get a data set that looks at that just has the past observations, you could actually do some analysis on it. I can't explain the pattern. I can't explain why. I can tell you why it snows, maybe generally, because that's a more meteorology question. I'm more of a climatologist guy, so. Yes.
Yeah, I was curious, what are the sort of standardization issues you deal with? Because obviously a lot of this is North America centered, but obviously can be used throughout the world.
Mm-hmm.
When you're, say, streaming in data from multiple different sources at times, do you find there's a lot of inconsistencies with the data formats that you're receiving? And how have you managed to find effective ways to deal with that? Since every jurisdiction may have their data structures
Yes.
in different ways at different times.
Mm-hmm. Yeah. So you mentioned you saw in the presentation the acronym CF used a lot. So these are the climate and forecasting data conventions, and that's been very helpful for the people who run climate models. So the IPCC, for instance, as well as Copernicus, and all these like the ECMWF. It's like the European Center for Medium Range Weather Forecasting. If we're all using the same standard, then we don't have to deal too much with the problem. So it's unfortunately not everyone uses that. So there are other libraries that we've been building to help deal with getting that data into a more conformant format. So there was one that I mentioned earlier, or I showed earlier, called Miranda in the top left. And so that's just kind of a data munging, but specifically for regional meteorology data. And yeah, that's a great question. It's something that we have to deal with a lot.
At some point you showed that you use X-ray and pandas.
Yeah.
What is your decision criteria which one to choose?
I think we are pretty much religiously using X-ray. And the reason why is because X-ray has very easy integration with Dask, which is fantastic for parallelization. It allows allows us to make use of high performance computing. So running climate analyses on computers that are 10,000 nodes. It is essential for doing that type of work. The reason we use Pandas. Pandas provides the conventions that we use for things like handling time specifically, so time series analysis. That's and essentially Pandas is running on top, is running below X-ray. So that's why we use it's very X-ray. Pandas and X-ray are very tightly interlinked. Yeah.
Have you considered Apache Spark, and if so, why didn't you choose it?
I think we have looked at Apache Spark for that, but our data sets tend to come in NetCDF format, and it's very easy to host that on the internet. There's software out there that allows you to very easily stream that, so stuff like Threads or the DAP protocol. It just ends up being a lot simpler to piggyback on all the amazing work that they're doing rather than do that. Oh, okay. Yeah.
Thank you.
Yeah, any final question? All right, well, thank you so much for being here.